Hello everyone, my name is Dr. Redwan Alqasemi, Professor of Mechanical Engineering Department at the University of South Florida. And today I'm going to talk to you about inverse kinematics. This is chapter 4 in your textbook. And we're going to first talk about and learn how to find the desired joint angles if we are given Cartesian pose of the end effector. So this is the inverse of what we typically do in the forward kinematics, where the joint angles are given and then we find the end effector position and orientation. In this case, inverse kinematics, we do the opposite way, which is if we know the pose or the position and orientation of the end effector, what are the joint angles needed to achieve that end effector position and orientation. So let's go through the learning objectives of this chapter. We're going to learn about solvability of the inverse kinematics problem, which includes, of course, from the perspective of workspace and degrees of freedom. And we're going to talk about the existence of a solution or non-existence of a solution. And if there is a solution, whether we have a single solution or multiple solutions, or maybe infinitely many solutions. So we're going to talk about all these things in the perspective of inverse kinematics. We're going to also look into solving inverse kinematics problems using algebraic methods. So this method will give you the solution for joint angles or joint values when you are given the transformation matrix. For introduction here, I would like to show some differences between chapters 3 and 4, forward kinematics and inverse kinematics. So in forward kinematics, which we have covered in chapter 3, we are given the joint angles, θ1 and θ2, and we are required to find the end effector transformation matrix or end effector pose that includes position and orientation of the end effector. So we run the forward kinematics so that we can find out the transformation matrix out of the joint values. Now in this chapter, chapter 4, it's the exact opposite problem. We are given the transformation matrix that's required for the end effector to go to, and I need to find the joint angles that would achieve that task of reaching that point or pose of the end effector. Okay, so chapter 4, inverse kinematics, given the desired transformation matrix at the end effector, find the joint angles or joint values that would take me to that end effector location. Solvability of inverse kinematics problems. So we're going to talk about this from different perspectives, whether we will have a solution or not. Of course, we all know that forward kinematics, you always have a solution, but inverse kinematics, you don't necessarily have a solution. And that's why we're going to go through looking at the solvability of the inverse kinematics problem. So the first thing we're going to talk about is the existence of a solution. And in order for us to look at this aspect of the solution, we need to define a couple of things here. The first thing is the workspace, which is defined as the volume of space that the end effector can reach. So if I demand the end effector to go to a point that's outside of its reach, there will be no solution to the inverse kinematics problem. Okay? So for a solution to exist, the end effector goal must be within the workspace. All right, so that's one condition that we should be fulfilling to find a solution. The second item I'd like to define is the degrees of freedom, and they're defined as the number of independent variables in a manipulator. Okay, so if I have 3 joints, that means I have 3 degrees of freedom. If I have 4 joints, I have 4 degrees of freedom, and so forth. Okay, for a solution to exist, the number of joints should be more than or equal to the number of independent Cartesian coordinates to be controlled at the end effector. For example, I may have a 3-joint robotic arm. I can only control 3 Cartesian coordinates at the end effector. In the case of a planar robot, I may have 3 joints, revolute joints in a plane. And in this case, I can only control the x, y, and the rotation about z at the end effector. So for a solution to exist, the number of joints must be equal to or more than the number of Cartesian coordinates that I would need to control. Now let's take a couple of examples here to show how this solvability issue can be resolved with the existence of a solution. The first example we're going to talk about here is on the workspace. So for this example, for the shown 2R planar manipulator, determine the conditions where the inverse kinematic solution exists. And here we have a planar 2R robot. We have joint 1 and joint 2. And we have the end effector right here as we see it. So to solve this, the inverse kinematic solution, for it to exist, the workspace boundary has to be determined first. And in order for us to determine the workspace boundary, we have to first freeze one of the joints and move the other joint. So if we freeze joint 1, then we can move joint 2, and it will form a circle of this sort. Okay? So we can take a measurement of the circle, and then we can move joint 1, and this circle basically will move around or orbit the origin of frame 0. Okay, so let's look at how this looks like. When the arm is fully stretched, that means theta 2 equals to 0. So the arm is completely stretched up. That means the end effector location relative to the frame 0 here would be the length of L1 and plus the length of L2. Okay, so that's the outer boundary, the outer edge of the boundary that we're talking about. Now, this plot here shows how this looks like. So this is fully stretched, and theta 2 equals to 0. So that length from the end effector to the location of frame 0, the origin of frame 0, would be L1 plus L2. Now to find the inner workspace boundary, then we fold the arm fully into 180 degrees. So the end effector comes down to here. And then at that state, we rotate the arm about theta 1. And then that would form a smaller circle right here from the end effector. Okay, and that would be the inner edge of my workspace. This figure here demonstrates that. So this is the first link. And then this red here is the second link. And when we rotate this about theta 1, it will form this small circle. And the radius of this small circle is L1 minus L2. Okay, so that would form the inner edge of my workspace. Now, for a solution to exist, the destination point for the end effector must be within my workspace. Okay, so if you look at this, this was the inner edge, the inner circle, and this was the outer circle. Okay, and that shaded area here is my workspace. So if the point, the destination point that I'm trying to reach is outside of this workspace, then there's no solution that exists for my inverse kinematics problem. If the point is inside here, inside that smaller circle, that means also it's outside of the workspace, which also means that there's no solution for my inverse kinematics problem. So for a solution to exist, my point that I need to reach will have to be within that shaded donut shape that would form the workspace for my robot. Okay. For the second example here, we're going to talk about degrees of freedom, an example about degrees of freedom. So for the 3R planar manipulator, the transformation matrix that relates the frame 3 relative to ground frame is defined as such right here. So when we use forward kinematics, we can come up with this transformation matrix that relates frame 3 to frame 0. Now the question is, can a solution exist if the desired transformation matrix at frame 3 is of the following form, and why? So part A here, we are given a desired transformation matrix that we would like our robot to go to. And for part B, we're given a different desired transformation matrix that we would like our robot to go to. So we're going to have to find out whether these would have solutions or not. So let's look at part A. If you look at part A, first of all, the format of the matrix here matches the format of the general transformation matrix that we have for the robot. If you notice here, the rotation portion here, the 3 by 3, it looks like rotation about Z. And in here, it looks like also a rotation about Z. Okay? And then the translation portion here looks like you have a value for x and y, and you have 0 for z. And here again, you have value for x and y and 0 for z. So let's look at how many equations we can extract out of this so that we can compare elements and solve for the joint variables. Now for this element here, element in the first row, fourth column, I have a matching equation for it here. So that's one equation. For the second element, which is in the second row, fourth column, I have a matching equation here. So that means I can form a second equation. And then from these four elements that I see right here for the rotation, if I look at the matching four elements, I can form one unique equation out of these. Like the cosine and sine are the same as these two equations, cosine and sine. So if I take one of these, I have the exact same thing for the other two. Okay, so if I take the cosine and sine of this first and second rows from the first column, I can match them to these elements, and that would form a tan 2 equation to solve for this angle. Okay, so that would give me a third equation. So out of the comparison of these two matrices, I can form three unique equations from which I can find joint variables theta 1, theta 2, and theta 3. Okay. So for part A, solution can exist because the robot is 3 degrees of freedom and we can extract three unique equations from the transformation matrix that we see here. Okay, and for that we're talking about an equation in X, an equation in Y, and an equation in rotation about Z. Okay, let's look at part B. Now, if you look at the format of part B, it does not match the format of the general transformation matrix for this robot. For example, if we see here 2 in the z direction, and we have 0 in the z direction here. And of course, 2 does not equal to 0. So that immediately tells me that this location here is outside of my solvability ability here. Okay, so for me to go to the z direction and have some motion in the z direction, I'll have to have joints that would go up in the z direction, which I don't have. All right. So from the format, and then besides, if you look at this looks like a rotation about y, and this looks like a rotation about z. So we know the planar robot cannot rotate about y. All right. So we know part B is not solvable because we don't have enough degrees of freedom to take me to that location. Okay. So part B, a solution does not exist because the desired transformation matrix requires the robot to move in Cartesian coordinates along the z-axis. And the rotation also is about y instead of about z-axis. All right, so this apparently is not something that we can solve using this transformation matrix. The second aspect we want to talk about in terms of solvability of inverse kinematics problems is having multiple solutions. So multiple solutions can exist if the robot can reach the desired goal in more than one configuration. So if I can reach my desired end effector goal, both in position and orientation, that means if I can reach it in more than one configuration, that means I have multiple solutions. Okay, and we're going to take an example and see what that means right here. All right, so if I have multiple solutions, I can have a finite number of solutions. Okay, and to have a finite number of solutions, I have to have number of joints in the robot equal to the number of independent Cartesian coordinates that I'm controlling within the workspace. Okay, so if I have 3 joints and I'm controlling 3 independent Cartesian coordinates, then it's possible that I would have a finite number of solutions. Okay. For example, in a 3D space, the maximum number of Cartesian coordinates, of course, would be 6 Cartesian coordinates, which includes moving in the x, moving in the y, moving in the z direction, or rotating about x, and rotating about y, and rotating about z axes. Okay, so this is the maximum number of Cartesian coordinates in a 3D space. Of course, if we're talking about a planar robot, then the maximum would be translation in x and y and rotation about z. All right, so if we have the number of joints equal to the number of Cartesian coordinates we're controlling, then it's possible that we would have a finite number of solutions for our robot. Now we can also have an infinite number of solutions for our robot to go to the exact same point in space. And this happens when the number of joints in our robot is more than the number of independent Cartesian coordinates that we're controlling within our workspace. Okay, in this case, we call this robot a redundant robot. For example, if I have 4 revolute joints in a planar robot, that means I can reach the exact same position and orientation of the end effector with infinitely many solutions for the joints. Okay, why? Because I have 4 joints and I'm only controlling 3 coordinates at the end effector, which are x, y, and rotation about z. And again, we're going to take an example to see how that looks like. Now let's take some examples about having multiple solutions for my inverse kinematics problem. So this is the first example here on finite number of solutions case. For the 3R planar manipulator, how many solutions can exist for reaching the same pose within the planar workspace of the robot? Okay, of course, I'm reaching the same pose within the workspace, and I'd like to check how many solutions would I have. Give an example of how to choose one of these solutions if you have multiple solutions. Okay, now let's look at this. This is a 2R or 3R robotic arm. Okay, we have 3 joints, joint 1, joint 2, and joint 3. And if you see here, the end effector is right at this point. Without moving the end effector at all, I can have this solution when the elbow is up, and then I can have another solution when the elbow is down that you can see here in the red dotted line. Okay, so both of them are valid solutions that would give the end effector the same pose of position and orientation. Okay, so I can have 2 different solutions to go to the exact same point within the workspace of this 3R robot. Now, how do we choose? This is an example here that I looked at. For example, if we're going from point A to point B, okay, and there are some obstacles here. Now, going to that point, I have 2 ways of doing this, 2 solutions. One solution is elbow up, and one solution is elbow down. Okay, just like what we saw here, elbow up and elbow down. So to reach point B without changing any pose to deviate away from point B, I need to choose one of these 2 solutions. Now, if I choose the first solution here where elbow is up, it's a fast solution or closed solution where I don't move the joints that much. But at the same time, it's not a safe solution because it will collide with the obstacles. Okay, now if I look at the second solution, I'll be traveling more. So this will be more joint motion to reach that configuration here. But at the same time, it's a safe solution that would not collide with the obstacles here. Okay, so how do we choose this? For example, this is one way of choosing the solution of one of the 2 solutions. Here I'm going to choose the safe solution because the closer solution would not be resulting in a safe motion. All right, so this is one way of doing this. Other ways may include efficiency in power or how much time it's going to take and so forth. So you can do all sorts of optimization to figure out which solution will be better suitable for your application. Another example with a finite number of solutions would include here a Puma 560 robotic arm. And what I need to show here, show 4 possible solutions for the same end effector pose. All right. So what I put here, I put this figure from the book that you can see 4 possible solutions. If you look closely at the end effector, all 4 solutions here show the same exact point of the end effector that's not changing at all. Okay, so the end effector is having the exact same pose or position and orientation in space. All right, so 4 solutions. The first solution here, the top left, the upper arm is outwards. So if you look at this joint here, the upper arm here is outwards or away from me, and the elbow is down. This elbow is down. Okay, the top right one, The upper arm is inwards, or it's towards me, and the elbow is still down. So that's a different solution from this one. The difference between these two is that the upper arm is outwards or inwards towards me. Third solution in the lower left here, the upper arm is outwards again, but the elbow is up this time. Okay, so the difference between this and this is elbow down and this is elbow up. Okay, that's a third solution. The fourth solution is when I have the upper arm inwards, or it's towards me, and the elbow is up. Okay, so the difference between this and this, again, is elbow down here and elbow up right here. So all of these four solutions are valid solutions that would take the end effector to the exact same point, but then the configuration of the arm looks different because the joints are different in each one of these configurations. Okay? Now here's another example here that shows this time an infinitely many solutions for the inverse kinematics. So for the 3R planar robot, how many solutions can exist for reaching the same point within the planar workspace of the robot? And again, I want to emphasize here the same point that includes only position, no orientation. Okay, so we're ignoring the orientation and we're only looking at the position of the end effector within the workspace. So this is our 3R robot. We have 3 joints, joint 1, joint 2, and joint 3. And we're looking at the end effector point right here. And we don't care about the orientation. So basically this gripper can be coming or approaching from any different orientation within that workspace. Okay, so basically we're controlling only the X and Y of the end effector. We're not controlling the rotation about Z. All right. So of course, in this case, since I have 3 joints and I'm controlling only 2 Cartesian coordinates, that means I have more number of joints than a number of Cartesian coordinates I'm controlling. So in this case, this robot is considered redundant. And of course, if it's redundant, that means we have infinitely many solutions for the same X and Y point that we are trying to reach within the workspace. Think about this with me. If I put a pin here at the end effector, if I pin it down, and of course I allow it to rotate, then I can still move this link right and left, which will move this link up and down this way, which will make this rotate this way about that pin that I just placed at the end effector. Okay, so since this can continuously move, that means we have infinitely many solutions without changing the X and Y location of this point. All right, so that makes this robot redundant, and it will have infinitely many solutions if I'm looking at X and Y within the workspace.